qPCR is an extension of PCR in which amplification of nucleic acids can be tracked in real time. Nearly 10 years after Kary Mullis's PCR discovery, in 1983, Russell Higuchi discovered qPCR by connecting the PCR thermocycler to spectropolarimeter. He used a double-stranded DNA binding dye to measure amplification by fluorescence. In a qPCR reaction, a reaction tube of DNA sample, a PCR buffer, Taq DNA polymerase, primers, and a dye is added to the thermocycler. In addition to dyes, probes are another method of detection which bind downstream of the primer. For the general protocol of dye detection, DNA denatures into single strands, then forward and reverse primers anneal, and then complementary strands are synthesized. As the newly duplicated double strand forms, the dye produces a fluorescence upon intercalating with DNA. Fluorescence increases as more DNA is amplified after each subsequent cycle. However, Taq probes use a different technique. During the annealing step, both the primers and probe will hybridize to the strand. The 5' end of the probe has a fluorescent reporter, whereas the 3' end has a quencher molecule that prevents fluorescence when the probe is intact. However, as extension occurs, when dNTPs are added to the 5' end of the probe, it's cleaved by the polymerase and the reporter produces fluorescence. Fluorescence for both methods are measured with a fluorimeter. This real-time detection of amplification cycles allows an amplification curve to be created. During the initiation phase, there is a low fluorescence signal and is not detectable. During exponential growth, fluorescence reaches a much higher level than baseline, in which the signal is detectable at the CT value. For quantifying the gene of interest, shown in dark purple, each reaction requires known concentrations and CT values for a separate reference gene and its serial dilutions, shown in green and brown colors. By determining the CT value of the gene of interest, this allows a standard curve to be generated to quantify the concentration of the unknown DNA sample. For real-world applications, qPCR is being used for diagnosing nucleic acid sequences involved in cancer and infectious diseases. In 2011, a qPCR assay test for influenza A was developed, using reverse transcription to detect for influenza RNA genomes. It can also be used to detect microbiota activity and diversity from environmental samples.
Created using Powtoon.